So today we'll start dynamic programming. Okay, so this is just introduction. It is similar to divide and conquer, but still there are some difference. Okay, that you will feel whenever you will start the course. Let me say about this topic. So I mean, mainly that in divide and conquer you divide the problems into sub problems, and then find out the solution of the two sub problems and merge the solutions together. Okay, so divide and conquer works top down, you know already this. And in divide dynamic programming, this is actually bottom up. Okay, in dynamic programming DP is it. So here what happens, you have to solve smaller size problems. In this case you will solve the smaller size problems, and then you will build the larger problem solutions from them. That means here one of the characteristics is that uh, uh, this is a generally optimization problem. What do you mean by optimization problem? Optimization problem is either you minimize something or say maximize something. Maximize something or minimize something. So these are called optimization problem, and dynamic programming is used to solve optimization problem. And in this what happens, if this is the large dynamic, this is the problem, then if you find out the solution of a smaller problems. These has also same characteristics as of the given problem P. Okay, and you first find out the solution of these sub problems, and these will be used so many times. So that means instead of computing these again and again the solution for this sub problem, you will store this in a table. In a table you will store this value, and suppose it is stored here, and whenever it is required you fetch the solution of this. Okay, if the solution of this sub problem is used only once, you need not store, but you will see in dynamic programming that the solution of the sub problems are are required again and again so many times. That's why you need to store the result in a table to save the time, to save the time complexity. Otherwise the time complexity will be very large, it may be exponential also. And obviously you need some space, but space is okay, better than time is very large. Space means you have to store the result in a table, to say two-dimensional table. It may take a big of n square, etc., like this. So problems have many solutions, so we want the best one. Okay, so you see, this is the bottom up, because dynamic programming, you please remember, dynamic programming is a bottom up. We solved the first the means sub problems, and then we take the help of this sub problem to find out the solution of the larger one. In this way we go on. But you another difference is that that you will see whenever you will learn the say matrix chain multiplications. In divide and conquer problem, what happens, this is the problem. In divide and conquer problem, suppose this is a problem and you are dividing it into two parts, this part and this part. Now these two parts are totally independent. The solution of this part, does not depend on it. Okay, so this is another characteristic of the divide and conquer. If the solution of one part depends on the other part, then you cannot apply divide and conquer. Now, to have a feeling of dynamic programming, you see one problem that is called rod cutting. You have been given a rod. You have been given a rod of length n and a table of prices pi for I equal to 1 to n. Say this is the rod. Okay, this is the rod, and its length is suppose 1, 2, 3, 4, 5 unit. Okay, and each piece means length of 1 unit is price of 1 unit length is say 10, price of 2 unit length is say 24. These are variable, these are not same. Don't think that okay, price of the rod of length 1 unit is say C, then price of rod of length 2 will be 2C. No, not like that. We are saying that as an input, we have been given you a rod of length n and the price of table of price pi for all this. So pi is the price of rod of length I, and these are variable. So you need to determine the maximum revenue Rn that you can earn by cutting up the rod and selling the pieces. For example, suppose I have given you a rod of length 4 unit. Okay, now you can cut it. You can cut it how? Integer wise. Either you can cut it into a length of 1 and 3. You can cut it into two pieces of length 2 and another 2, or you can cut it into a piece of 1 and 2 unit lengths, like this. You cut and you sell the rod pieces and you will earn something. So what will be the profit, maximum profit that you can earn by cutting the rod and selling the pieces? So if you see here, if you do not cut the rod, then you will earn what? You will earn what? P4 equal to 9, because I
So
am
the
not
summation
cutting.
of pieces.
Summation of pieces means here you see
Yes.
P1 means P1 is price for 1 unit length, price for 2 unit length, price for 3 unit length,
Oh,
price for 4.
acha, acha. Okay,
Okay,
sir.
is it
Got
clear?
it.
So you will if you do not cut, that means the whole length price is 9. Okay, n equal to 4, the length of the rod is also 4. You check the rod of length n. This is very important. And pi is the price of each length I. Pi is the price of rod of a length I. So if you cut into 4 pieces of length 1, then you will get what? 4 into 1. You will earn 4 unit. Now if you cut it into 2 pieces of length 1 and a piece of length 2, okay, means you are cutting it into 2 pieces of length 1. That means 1 and another one is of length 2. Clear? So this one length has the price 2 into 1. Clear? And P2, this is length 2. Length 2 has price 5. So 2 into 1 means 2. Just a minute. 5 plus 2, 7. It should be 7, I think. I
Yes, sir,
think
there is a mistake, sir.
it
It's
should be 7.
seven,
Nah?
sir.
It should be
Seven,
7.
sir.
Yes,
Seven,
yes, yes.
seven, sir.
There is a mistake in the slide. So it should be 7. And if you cut into 2 pieces of length 2, then it will be 2 into 5, 10. Okay. So you see, in this way you can cut in some other ways also. Say you can cut a piece of length 3 and 1. So that means 8 plus 1, 9 in that case. Clear? So there are more options, but the maximum revenue that you can earn is 10 in this instance, for this instance of the problem. Okay, for this input, the maximum revenue is this. Now the question is that here n is 4, but n may be very large. So how can you cut and sell the pieces so that you earn maximum revenue? This is the question. So in general, a rod of length n can be cut into 2 to the power n minus different ways. Okay, since we can choose cutting or not at all distance I. There is a length. Okay, now here you are, in this case this is the I length. Okay, here you may cut it or you may not cut it. There are two options. So in this way, two options are there. So you know that means 2 to the power n minus 1 different ways are there from the left end. From the left end. Okay, I is 1 to n minus 1. So you see, if you see all these ways and then find out that what will be the maximum revenue that you can earn, then that will be, you see, it is already exponential. If there are 2 to the power n minus 1 different ways and you are applying all these and then choosing the minimum one, maximum one, then automatically the time complexity will be exponential. Clear? Now that means here we can calculate the maximum revenue Rn in terms of optimal revenue for the shorter roads. So you see, Rn is the maximum of Pn if we do not cut at all. Otherwise, R1 plus Rn minus 1 R2 plus Rn minus 2 plus in this way this. But here you see, means we have not chosen that there are some other ways also, means say R1, then again another means 2 3, means here you see the partitions, you can think that's just two pieces. So another approach is what? Set R0 equal to 0 and this maximum of Pi plus Rn minus y. So cut a piece of length I with remainder of length n minus I. And only the remainder means you are cutting it into two parts. Here it is I. Okay. So this length is of length I, and the remainder, this portion is the remainder. Now what it says that you cut into two pieces, then you can recursively cut the remainders, but not this portion, this portion is fixed. In this way you choose, means Pi is fixed. Okay, from this you will get the profit Pi, and you see all types of partitioning here and find out the cost. So only the remainder, not the first pieces, may be further subdivided. This obviously, if its length is I, then its length is n minus I. So this you can further subdivide. So that's why it is Rn minus I and Pi. Pi is the, if you do not cut them. Why I am writing here Pi? Because P symbols means we are not cutting at all. So Pi, we are not cutting this at all, and the length of is I. So you can write an program also. If n equal to 0, then return 0. Else q is minus infinity, means I am taking the cost, q as the cost, that I will return. And for I equal to 1 to n, okay, 1 to n, not means this is the length. So here 1 to length 3 in this way. Okay, so up to this n. Q will be maximum of q comma Pi minus 1 and this portion. Pi means 1 up to this, and you recursively compute for this part. You see, this is the recursion, cut rod, P length n, P length n minus I, and you are adding with this Pi, and you compute, and in this way you go on, and you will find out the maximum, and then you find out, you have to consider all possible subsets. Now how much time it will take? You see, Tn is the total number of calls made to cut rod. Basically here the time complexity depends on how many times you are calling this function. How many times you are calling, because these are the constant, constant. You check, it is constant. These are so mainly this portion, how many times you are calling this recursively. So here you see, if n is 0, then I will return this. If n is 0, then only 1. Cost is constant. If n is greater than 0, then what? This will be just 1 plus, means some cost for this. Okay, means here in this case you know that this will be called, so 1 plus this n minus I, or 1 to this. So you can write like this. So what will be the solution for this? The solution for this recurrence will be this 2 to the power n induction. Can you tell me how can you prove this? This is 2 to the power n using induction. The steps has not been shown.
So take like 0 as the base case.
See, if it is correct, then you can replace this formula at the right hand side. Means 0 to n minus 1. Check it. We are assuming that it is correct for j less than equal to n minus 1. It is correct. This formula is correct if for any values of j less than equal to n minus 1. So you replace it here. So it will be what? 2 to the power tj, see tn. So I am assuming that this is correct. So if you put it here, you will get what? 1 plus, then 1 plus, means I am writing here in this way. Say 2 to the power j plus. In this way you count, and how much, what will be the value, check it. And j is n minus 1, so you have to put it n minus 1 here, actually not j minus 1, n minus 2. So that means 1 plus 2 to the power n minus 1 plus 2 to the power n minus 2. So how much this is? Tell me. What is this value? This is basically Tn I am computing. Tell me. What is the sum of this dp?
Two power n.
2 to the power n. Means you are telling, suppose n minus 1 is 3. Suppose that means 2 to the power 3. 1 plus 2 plus 2 square plus 2 to the power 3. Is it 2 to the power 4? Or say 1 plus, this is nothing but like this. Say 2 square plus 2 plus, where you are adding, and you are saying that this will be 2 to the power n. So is it 2 to the power 3? I am asking. Is it correct? Or 2 to the power 3 minus 1? Check it.
Minus 1, sir.
2 to the power 3 minus 1.
So 2 to the power n
2 to
minus
n
1.
minus 1.
So 2 to the power n. So we have proved. Now this is exponential, and this will take a lot of time if you follow this. So it is not possible. Now why it is exponential also? There is a reason. Check it. See what you are doing. You are see this value is variable n minus I. So initially the length, if suppose the length is 4 unit, okay, n is 4. So then you will call what? This is the length 4. So if you cut it here, means it will be P1 plus R3. Or if you cut it here at the unit 2, then it will be remainder 2. So P2 plus R2. This, if it is you cut it at this place, then it will call this P3 plus R1, and if you do not cut it at all, then you will call this and it will automatically terminate. Now P1 plus R3. Now see, so here 3, n value is 3. Okay, recursive. So again it is possible for these 3. Okay, 3, you check it, it will be P2 plus R2, 3 units. So this, okay. So in this case, you see, if you cut it here, goes there. If you cut it here, goes there. If you do not cut it at all, so like this, again you will expand this recursive call. These are basically recursive call. And when it is 0, it is not, no recursions are called. You check it, when n is 0, no recursion. Otherwise, you are calling. Okay, I equal to 1 to n minus 1, you are calling. So you see, if it is n, then you are calling it with how much? That n minus 1. I value is 1. Then n minus 2. I value is 2. N minus 3. N minus 4. In this way you are calling. So that's why if it is 4, then you will call it with 3, 2, 1, 0. Whenever the argument n equal to 4, then you will call it 3, 2, 1, 0. Okay, is it clear? N minus 1. Then when it is 3, you will call it 2, 1, 0. When it is 2, then you will call it 1, 0. 1 means 0. Like this. So here you see it is P2 plus R2. Here P1 plus R3, P2 plus R2, P3 plus R1, P4. And in this case, P1 is already there, and you are now doing for R3 the rest of the three parts, these parts. So it is P2 plus R2, okay, then P3 plus R1, then P4 plus R4. I mean, in this way you just compute. Now here you see this thing, check it, and this thing. Are not they same exactly?
Yes, sir.
Yes. So that means you are computing the same thing twice. When n is 4, but you see, if n is 10, then there will be so many such calls who are exactly similar, and you are calling them more frequently, and that will be wasted of time. So why you are wasting all your time? This is a sub problem. This is the sub problem, and you are optimizing this also. So you find the solution for these sub problems, store it in a table, and whenever you require it, you fetch the result from the table. You just compute only once, never compute it again and again. This is the idea of the sub problem, means dynamic programming. But please remember all this. For example, you see in this case also, say this 1, 0, 1, 0. So these 1, 0, these are called again and again. Okay, so this is this again and again. So you need to first solve the smaller sub problem. Then with the you solve the next larger sub problem that will require the smaller solution of the smaller sub problem. Then you, so that means the solution are like this. In this way, you are computing. First this one, then this one, then this one, say like this. So after solving a sub problem, store the solution. Next time you encounter the same sub problem, look up the table or solution, instantly solving it. But here only one drawback is it needs space. But that space is far better than the time, obviously, because you have a lot of space nowadays in your computer. Okay, so table needs. So the two. So that this is the dynamic programming for the rod cutting problem. So I am not interested too much about this because there are so many interesting problems for use that use the dynamic programming. For example, a matrix chain multiplication problem, 0, 1 knapsack problem, and then say all pair shortest path problem, graph theory, and so on. Similarly, there are say a set of a polygon has been given. You draw the triangles by drawing the diagonals in such a way that the length of the perimeter of all that sum of the length of the perimeter of the triangle is maximized. Suppose that is so. This type there exist so many problems. Now, we do not know how many problems exist that can be solved using dynamic programming. More than 100 problems exist, I'm sure. 1,000 it may be. So means always see that if you cannot solve, means if it needs exponential time to solve a problem, then think, can it be solved using dynamic programming? Here that means Ri is the maximum profit. First you compute the Pi is the problem inputs, then Ri is the maximum profit from cutting rod of length I. Then goal is to calculate Rn. So Ri is defined by this, that you know. Iteratively follow in Ri table by calculating R1, R2, R3 in this, and Rn is the final solution. This one is the final solution. Here you do one see one thing. In this case, check it. Are there any recursive call in this function? See,
Sir, could you repeat the question, sir, once?
I am asking that are there any recursion means function call here in this code?
No, sir.
No, sir.
No, sir.
No. Here you see just R table. This is the one-dimensional table. Table array, basically array. Check it. No function call. But here you see this was the cut rod same function call. So that means recursions that you were using, note it down, that you should not use here. Okay, otherwise it will call again for the small values. Are you getting what I am saying? So that means for the small values, if it has not been computed, you compute it and store it in a table. For example, here check it. R0 is 0. R0 is 0. Now you are computing for j equal to 1 to n. Okay, array R0 to n stores the computed optimal values for R0, 0 for R1, R final value Rn, you know. So that you will return Rn. Now for j equal to 1 to n, you see what happens. I equal to 1 to j, so j is 1. Okay, so in this case q will be max of this and p values that 0, and r of j and I are same. Okay, I is also 1 and j is also 1. So that means 1 minus 1 is 0. So you see this is computed and you add with this and store it q. Then R1 will be this q. Clear? So you see that we took the value of R0 and computed the R1. Then again the R2 will be computed, R3 will be computed in the same manner, R4 will be computed, and finally Rn will be computed. Consider the problem in increasing order of size. All you need to consider decomposition. Okay, you check it. I am not explaining. It's easy. It is n square because here j is of order n, and this is also n times. So therefore, it computes. So this is the idea. I am not explaining it in details. So in next class we will take means the next problem, that dynamic programming matrix chain multiplications. Okay, this is just introduction. So now there will be a series of lectures on dynamic programming.
Yes, sir.